fairly simple kind of vertex operator in disguise. Right, so what we had, just remember last time, was H was L2 of S1. We had this projection of L2 and S1 onto the Hardy space of S1. And then we decided that the restricted unitary group acted projectively on Fock space. And even and equally well, we could make sense of complexification of this acting by just considering in between the standard basis elements of this. Let's now take, as we could equally well take a variation of this, which would be just to take almost 2, and then the whole and the Hardy space projection replaced, we just take 2 copies of it. Well, then on this space here, we have the loops of the circle, which are just the C infinity maps of the circle into U1. So the complex numbers of modulus 1. They act by multiplication. And the orientation for observing diffeomorphisms also act on L2 of S1. Initially, if you just change the parameter, it won't be unitary, but then correct by a Radon-Hickman derivative, these act unitary representation of this thing just by reparameterization. And this obviously forms a semi-direct because the diffeomorphisms act as automorphisms on loops just by reparameterizing a loop. So we have and then the remarkable thing is that these commute with P modulo the Hilbert-Schmitz. So they give rise to a unitary representation, projective unitary representation of this into the projective unitaries on Fock space. Well, equally well, if we work in the slightly larger model, so for H2, then the same will be true for L of G, loops of G on this, with G equals SE2, or U2 if you like, and L of G the same thing. These are just the loop groups. You have the projective representation. The Fock space for H2, because it's just a direct sum of 2 H's, and physics is a functor, then this is just this is just the tensor product of 2 copies of Fock space. Right. Well, so these, but in particular, SU11, these are just Möbius transformations of S1, which these extend, of course, to C, preserving the inside and the outside of the disk.
How to describe this first? I mean, the geometric group theory people also use it.
Use what?
The commutate with, P.
Well, this This, oh, you mean who, for the diffeomorphism group?
Yeah.
Well, I mean, I think the traditional figure that is quoted, I mean, as in group theory, as Kajnan, I mean, he gave various methods of doing it, but I don't quite know how it filtered through to people like Graham Segal on that analytic level. I think it happened through Kajnan, but of course, people in pseudo-differential operators, it's the invariance of the pseudo-differential calculus. So I assume various disjoint groups of people knew it separately, and each had their own technology for proving it using the minimum of theory from somewhere else. I mean, it's actually fairly, you can.
It's very easy, yeah.
It is. I mean, if you do the Cauchy kernel thing, then it's not very hard. If you work with a Cauchy kernel, that's the easiest way of seeing the diffeomorphins. The other is just turtlets, of course.
You have to correct for the radar mechanism.
But that's just something, that's just multiplication by a function. So that's smooth. So it just reduces to doing a straight change of variables. And then if you use the Cauchy formula for the projection, then you can just compute the difference of the two things and see it's Hilbert-Schmidt because the singularity disappears. So that's one proof, for example, in Graham's book.
Do you know what is the regularity needed for this one for that to work?
Very interesting. Well, I think it's the normal thing that happens here is the 3 over. Here it's the Sobolev half norm, which governs it. And here there's a very interesting paper of Nargan and Dennis Sullivan. And I think it's the 3 over 2 norm, but there's Sobolev 3 over 2 norm. If you just regard them as maps on circles straight like that.
That's the Rabi-Kaplan derivative will be a first derivative.
Yes, but even without that, just this. So it's definitely the uniform. So what's easy to show, even I can do it by hand, is that the unit, it's the topology from that is the uniform norm. It's stronger than the uniform norm. It's not true for the loops. That's quite important.
It's
They're
enough,
not important here.
it's enough to have like 2 plus.
Yeah. But that makes a diffeomorphism group a little harder topologically, but in the end that's not how you sort of do it. But anyway, going on with this. So I think this then acts canonically on F, meaning fixing the vacuum. Which, if you remember, was this. Because it actually commutes with the Hardy space projection if you write it down properly. And then, in general, if you take the infinitesimal generators for this, that will be I d by d theta, which is normally called L0, L1, L minus 1, and, well, these will be the generators, the infinitesimal generators of SU1 acting on the circle. Then you get operators L0, L1, and L minus 1 as the on Fox space. So these are on circle, and these are on Fox space. And these kill the vacuum because of infinitesimal, so Ln omega equals 0 for n equals 0 or plus or minus 1. Right. So that is that. Now, if we just look at the rotation group, so the rotation group will just be generated by these things. Then Fox space breaks up either this Fox space or it breaks up as a direct sum. In the way that I'm doing this is kind of funny because it will be n plus a half, but it's in this set, 0, a half, 1, 3 over 2, etc. Where these are eigenspaces of L0. Physics, an L0 restricted to Fn is multiplication by n. So n is a half integer. And these dimensions of these Fn spaces are less than infinity. So this is what's called a positive energy representation. And now, if we extend so the Lie algebra of the diffeomorphism group is just the vector fields on S1, and if we, its complexification as basis ln, which is I e to the n theta d by d theta, and the corresponding operators have corresponding operators ln on Fock space, which correspond to those little ln's. Now, the little ln's, if you compute their brackets that you just do as vector fields, and I hope I get this right, it's just like this. And the representation is projective, so that implies that ln, this is true, the same relation is true modulo a scalar, and there are fixed operators that define this, and then you find that the rule is right. So this is what's called central charge 1. Similarly, in the case of the loops about the loop of U1, you'll have an operator x of z, you'll have operators an, which satisfy an equals delta m plus 1 times the identity. This is just called a boson. And then here, so this is the transition to conformal field theory and vertex algebras. Here, I define a generating function which just puts all those operators together. That's often called the stress energy tensor. But for the moment, that doesn't matter. Here, we'll assemble these into a generating function, and this is called a current. Similarly, for the Lie algebra of L of SU2, well, it'll be a similar thing to this. So for each, we'll take the basis, we have the complexification of SU2, so we can extend the representation to that, and then we'll have operators, similar operators like this for each element in the complexification, just so the trace zero matrices in 2x2 matrices. That's the complexification of its Lie algebra. So again, things which are right like this. And the relations, these are just the Kac-Moody relations. And they are just a kind of SU2ization of that. So So this is like, this is just how, if you have just matrices x e to the in theta and y e to the, x e to the in theta, y e to the in theta, you get this when you took the commutators, just regarded as matrix valued functions, and then this is the cosine. Again, so it's just a scalar, and that's a central extension. Okay, right. So, well, these, the representations on f tensor 2 of L of SU2 break up, and we can put the rotation group in as well, break up as the direct sum, of two irreps. And each of these, so we call them H0 or half, HI, I equals 0 or half. This can be decomposed as this time, where L0 acts as H plus N on HI plus H. Let me just write it like that. Each of these are finite dimensional. And these are the eigenspaces of L0. These are integers. And HI 0 is just the complex numbers, a trivial representation. HI, so H0 and H half 0 is just V half, the two-dimensional representation. Now, in general, so if we take L greater or equal to 1, and then form f tensor 2, just compose it L times, then we'll introduce a factor L here in this. If we just take the tensor product, then we need a factor L, need to introduce a factor L called the level in this thing star. And then we can do the same thing with decompose the level L representations of SU2, LF SU2. So level L, these representations have a similar decomposition to, so HI, where I now lies between 0 and L over 2, and HI 0 is just the 2i plus 1 dimensional irreducible representation of SU2, and this is as constant loops. Constant loops commute with rotation, so L0. So each of these is a module for SU2, and in that case, and these are all the positive energy reps of SU2 at level L. There wasn't some multiplicity, but with infinite multiplicity. I mean, if you were to do this properly, the commutant that we were talking about before will be given SU2 at level L. You'd have in the commutant will be generated by SUL at level 2 plus SU1. So that you can everything will be explicitly labeled. Everything has been done by Tsuchiya. So these are pure infinite multiplicity. You just pick, for each of these irreducible representations, you can pick a generating at least one vector explicitly in the box space tensor problem to generate.
No, actually,
It's actually in my paper.
right. So only the isotopical thing you can
The isotope, yes. I mean, once you know, it's a multiplicity one thing. If you decompose them with respect to loops on here, just taking the case of level 1, you have an extra loops on U2 act irreducibly. So you get the help, so they act irreducibly on F tensor 2. So if you take L of SU2 and L of U1, which is the center of U2, then that decomposes as two representations and you can explicitly say what they are. This is an advertisement. I gave a course earlier this year, which can be found on my Cambridge website, which does does this decomposition at level 1 explicitly. And most of what I'm going to say is not analysis. Right, so now that's a kind of Lie algebra picture, and then the subfactor picture that came from this is as follows. So the Lie algebra picture we'll see in a minute is completed by defining vertex algebras. Now, actually, vertex algebra is slightly tricky to teach, but there are two kinds of vertex algebras. The one we'll see today, so fermion vertex algebra, which is rather ancient history. It sort of somehow predates even bits of string theory because of known techniques in physics. This sort of would be sufficient. Knowing this algebra will be sufficient to do all the classical groups. If you wanted to do the vertex algebras, classical groups. So once you've done the work for one, that implies everything else because they're kind of contained as sub-algebras of tensor problems. So that's quite good to know that you just have to do this baby example, classical groups. And then the other ones, well, there's the vertex algebra of a lattice. And that was mentioned sort of en passant by our Alberto friend. So E8 would be an example of this. E8 can't be constructed below level 20 or something, so something or 12 or God knows what, using fermions, but it can as a bosonic description. That is because this group, what does a bosonic description mean? Well, you have a compact Lie group, you always have a maximal torus. And at level 1, the theorem is that for the level 1 representation of this is only 1, this acts irreducibly. And so this theory is essentially the theory of a lattice, because a torus is described by a lattice, and that's why this is so. So that's the simple, if you like, explanation for this acts irreducibly at level 1. Right, so we'll talk about that in a bit. As soon as we come to vertex algebras, these will be like algebras, so we'll have all the notion. I think Richard Orchard once showed that they were Lie algebras in a certain category, and then that was kind of dropped because it was too unpalatable. But I think now it would be fairly palatable, by the way, for using the category. It would be considered charming and aesthetic. Okay, so we have modules, intertwiners, and all sorts of things like that, and just like ordinary algebras, and those will be the things that are necessary to do. These intertwiners are sometimes called, the most important ones are called primary fields. But I'm distinguishing modules and primary fields. Because primary fields go between different modules. So unimportant. The labeling of the primary fields is the same as one of the labelings of modules. Okay, but let's just go back to analysis and subfactors. So I'm going to sort of just very briefly say what goes into constructing the subfactors for loop groups, or in general things, conformal field theories. Now, we've heard about nets. I don't actually use the language of nets, although they're in my head. So, for a loop group, how do you find a net of finite algebras on the circle? So you have an irreducible representation of a loop group on a Hilbert space. And then you can define a subloop group just as these are all loops which are trivial equal to 1 on the complement of an interval. And then, although this is a projective representation, we can still define the double commutant unambiguously, because something commuting with an operator or a scalar multiple of the operator really doesn't change it. So the double commutant. And this is a net of Riemann algebras. That's the sort of thing that's being talked about. And I mean, essentially, one of the things is that this net, knowing this net without knowing the loop group, but you could presumably compute all the fusion rules and subfactors, but unfortunately that has not been done so far. There's only one way of, at the moment, of computing any of these fusion rules. So, okay, so that's these finite algebras, and then what happens here is by locality, this is contained in the commutant of the interval. So this was something that Fornadai worked out in Paris in something like 1988 or 89 after a common seminar. Well, I think I was asked to speak before we knew anything. It was amorphous, a little, which I got, yes, he told us to use fermions. Right, so, okay, so this is an inclusion of a fact of type 3-1 factors that Vaughan and I defined, and this should be, the idea was then to decide how that would be, how you could unravel that. And the secret to that was confusion, which I'll briefly define, just so that we have a kind of data. And so here, so we have, in the theory, we have a distinguished representation, namely the vacuum representation, which is the one for which the trivial part, the rotation fixed part, is just C, the trivial representation of SUT. And I'll run C omega, trivial representation of SUT. Well, then, of course, in finite algebras, all sorts of things go on that. We can do Tomita-Takasaki theory on this. I'm not going to tell you what that is, except it's very simple in this case. But that enables us. So this is because it's got this vacuum, we can apply modular theory of finite algebras. And that enables us to define this definition of confusion. So given two representations, H1 and H2 at level L, then we take operators, and call them X and Y. We define operators H0 to X, which commute with LICOG. So these and Y and then we define an inner product on these. So somebody at some stage talked about a relative inner product, which I think that name is attached to taxonomy, but the truth of the matter is that in order for us, or at least for me, to be able to work out how to do this fusion operation, I got private notes of Alain Kahn, which partially got written up by Sauvageau, but not entirely. The notes were incomprehensible to me because they were a kind of unsymmetric definition of the tensor product. But after thinking about it for long enough and using the wrong definition, we then got this definition. But, so those notes of Alain Kahn were very important. They gave 3 or 4 different ways of looking at fusion. He was doing it for different reasons. But I don't, in the 2-1 case, it wasn't important. In the type 3 case, it was very, that was very influential. He thrust them, as that means, like a slightly more implied than the CAR. Anyway, so if you complete this, and that defines the fusion dimension 1. And there's a method of doing this with fermions. If you were to do this fusion for fermions, then you would just sketch what would sort of happen. That you would have a fermion here, which is concentrated in an interval I, in order for it to commute with fermions in the opposite interval. And here, something, so this is F is just a function on the smooth function on the circle, which is 0 off IC. That will be what happened for fermions. And then G similarly, so G is concentrated, F is concentrated here, supported there, G is supported there. So as fermions, they anti-commute. And then the confusion, you simply take these to their composition, apply to the vacuum vector. It's as simple as that, possibly with the sign. And that will be the map that for fermions, if you were to do this fusion for fermions, taking fermions in 2 half intervals, if these were graded, you'd have to have some signs in here. You put -1 times the sign of these two. So that's sort of a standard thing for anything that's graded. And then you would compute fusion. You'd compute that the fusion of Fock space with itself gave Fock space. Because there's only one irreducible thing, so you're not doing very much. But that's what it is. And this is the idea that somehow you see this. In the more complicated cases of SU2, you won't just have ±1. The fields, when they move past each other, will become braided. And that is how all the other representations will occur. So I'm not going to go into that. I'm going to concentrate henceforth on fermions, which will be a guide to principles of finding operators, primary fields, and things like that. But there's this kind of, if we add all the braided tensor category kind of declaration, that this modulo that declaration is identical. So in this case, if we when we do this, so we'll find just in a scheme like this, that this and that this, at the end thing, we have just a truncation. Compute the quantum dimensions of these, and they've listed in sort of finding the unique positive dimension which makes that work properly, given the dimension at H0 is 0, so it's just a Caron-Frobenius graph. Compute that. Okay. So there's some analysis here. And the main thing is the x's, or y's, will be smeared primary fields. And so we somehow need to relate this analytic picture to various algebraic things which exist in the world of orchards and beyond. So vertex algebras, primary fields, and that, I mean, at the time we were doing it, that had been written out explicitly by Tsujiro and Kanye for SU2. And I think Vaughan had noticed that the braid relations were the same as the things that he'd found and Hans Fensel had found. And so the question was there.
Sushi and Canning were written.
Yes. Well, yes, they wrote it in their paper. And yes. Okay. So now we want to describe how to say what primary field, what vertex algebras are. So very quick resume of vertex algebras. So as I say, these are in the notes of the course which I sort of have in front of me. So on Fock space, we have operators psi z equals some en z to the minus n. And so this is the generating function for fermions, and the duals. And we computed the 2-point function. Which was, we kind of, when we did the expansion of this, we assumed the modulus of z is greater than the modulus of w. Well, it's not very hard to see that, well, if you can compute this, for any psi and eta, just any finite energy vectors, that means linear combinations of the basis vectors. So these are the sums of eigenvectors of L0 on that thing. The eigenvalues of L0 are called the energy. And what you find is this satisfies the same thing. It's a function, it's in Cz, so it's a polynomial in that with a pole, and then we have 1 over z minus w. And it has a pole, as you expand it in this way, there's only one z minus w. So the same singularity, just so the pole at z equals w is a simple pole. You can do the same thing for the xz's, but this is just the key to this. Now, in general, given operators az, and bz, bw, bn, w to the n minus 1. If you assume that the an's and bn's, well, let's say an is equal to n plus kappa an, sin n, or alpha. And similarly for bn, I mean a minus n here. So you assume some condition like that. That's just saying that these are, under commutation, these are kind of eigenoperators of rotation, which the psi-n's are. Then in general for vectors, you will assume that these functions in z greater than w agree with a rational function, I'm sort of, you've all eaten ravioli. I'm showing you what goes inside it, which you probably don't want to know, because it could be things that you wouldn't eat normally. Creatures. Critters. So they agree with a rational function with, so if you write it out, it's like that. And then 1 over z minus w, with where the z minus w has a fixed pole for all, so where the pole in 1 minus z w to the k, this is fixed for all psi eta. Okay.
Never gets bigger than K.
Sorry? You get bigger k's.
Sorry?
Sorry?
Never gets bigger than order K.
Yes, it's fixed for all sine eta. There's a fixed k which works for all sine eta.
You could have a small one.
You could have a smaller, yes. I mean, it could vanish for certain things. I mean, for example, if you took two fermions with a vacuum vector, psi z, psi w, then clearly they would go to, they'd be orthogonal to the vacuum vector. So you just get zeros out. But still, it's essentially a z minus w. Right. Well, so if you do now, then there's just a simple lemma that you can prove. But if you expand this, we have this expansion of the range ZW. Now what you find here, with these, if I switch Z and W, then I get a minus sign. So this is equal to, so this is in the sense of matrix coefficients, so I'll put them in. This is equal to EW AZ. And then a plus or minus, depending on fermions, you get a minus sign because you're permuting two fermions, depending on the sign of the operator. I mean, this is a Z2 graded theory. So this would be true in W greater than Z. And then near the singularity, you could write this as a sum of AK C. Like this. P less or equal to K, Z minus W to the P. Right.
So the meaning of that equality is it's the same rational function.
It's the same rational function.
To say that it's equal to different values, you don't have those you can't see.
In fact, Vaughan is making a very good point that if, so the way we get back into normal field theory is that if suppose we're given a function f of z, which is sigma a to the n, z to the n, smooth function on circle, then in physics you define a field, the smeared field, as sigma an times, well this is a bad thing, I'll write capital AN, where A is equal to sigma AN, z to the minus n minus 1. So I'm thinking of this, now this is then really think of it as an operator value distribution. This is now an operator. And then this relation here will become, if F is supported here and G is supported here, just like for fermions, then this would say that this is equal to plus or minus AG AF. So the rational function thing is the algebraic version of this locality result. And so, in one sense, you can think of these as operator value distributions, but perhaps not always. But when you will use them ultimately in that way in the end. All right. Well, now, so this is called the operator product. So you could write this as AZ, CP is often written as A orchard product with B, and then you write AZ BW is tilted to sigma A P B W over Z minus W to the B. There might be a factor of 1 missing there. And that's that. Right, so this is a way when two field operators become very close that other operators come out of them. Now, when that happens with primary fields, which have the sort of representations attached to them, then you might draw something like this. So a primary field of charge I and charge J gives something charge K. And the way physicists understand that is that they put primary fields that correspond to this operator here, operator I, operator J, and then they see the kth operator appearing in the singular terms of the product. And for them, that is fusion. So the operation of fusion is this operator product expansion for them.
What's the interpretation of the fusion multiplicity in this?
Well, you get several different fields appearing on this side. You can number them. But usually, in nice cases, you just do it as multiplicity 1. But you could get several possible primary fields appearing, and then you have to count those. But usually when we do the algebra, though, we try to do the multiplicity case 1 first, like tensoring with the two-dimensional representation of SU2, and then that, of course, generates everything else. If we have multiplicity bigger than 2, we are often in deep problems, because it's very hard to show you get everything in a tensor product. Anyway, operator product expansion. Well, what happens here, so these operators, the operators that you get this way, you can start off with fermions, you can multiply them together. So for an example here is the operator product expansion that you would get if you do this with fermions. I can't read my own writing. Right. So this is the generator of the Virasoro. This is just on ordinary Fock space. This is the Virasoro thing that I wrote down with the LNs, and this is the derivative of the ANs, little ANs, the algebra of U1 has. And then that just goes on.
Is that square?
Sorry?
Is that square thing?
Yes. Yeah. No.
So it has to change.
No,
size
actually,
to
no.
get-
I think you're right. In fact, this is completely wrong.
You're right, Rosa.
Yes. I'm sort of reading from the wrong line. My glasses broke about 2 weeks ago, so I can't see anything. It's also unclean. Right, So part of this was correct. Right. So here you get the thing that we just computed. That gives the 2-point function. There's all the other things. When I take the vacuum with them, they vanish. Then I can produce this. First produce the bosons from fermions. That's part of the boson-fermion correspondence. And then I can produce a quadratic formula for the Virasoro thing in terms of fermions. So that's all hidden in that. So these things encode things which are quite, you can prove them by hand, by being sly, but it's better to do it this way. But even better is that, so what turns out, so if you continue just composing these things, you can get lots of operators. So the operators V, A, Z, they have various properties. Well, they satisfy L0 commutator AZ equals Z d by dz plus alpha prime, which is related to the alpha I wrote down before, times AZ. That's just those commutation relations I said at L0, its ANs satisfy a similar thing. That's true when you do this operator product expansion. They satisfy what's called the equation of motion. So with L minus 1, this is the easiest. Just that. And they commute and anti-commute with each other. So the AZs commute, well, it's graded commute with psi z, psi star z, and all the other operators we've created, all their descendants. Well then, there's the theorem.
Sorry, what was
A of z is any operator we produce this way. So we produce a set of operators this way, just by, and they will have these properties. Well, then there's the Peter-Godot philosophy. There's something, well, the Peter-Godot test. If something looks and smells, could you switch this off, please? Like a vertex operator. It is a vertex operator. And what does that mean? Well, the vertex operator is, if I take it, A of z, and I apply it to the vacuum, and I set z equals 0, this will create a vector A. So the claim is, if it satisfies these conditions and creates the vector A, it's unique. So if A satisfies the conditions dagger, and creates A, it's unique. Well, all states in F can be created for vertex operators. That is justified sort of.
What is alpha prime in the first?
It's something that's related to alpha, but I'm not going to tell you precisely how.
What's alpha?
Alpha, when we took the nodes, I said that L0 AN was equal to something like minus n plus alpha AN. So that was just, it's essentially, this should be the eigenvalue that L0 has on A, on the state created by A, or plus or minus 1. So, well then, we can label the vertex operators by V of then, if we, the amazing thing, so this is called the Borchard's associativity formula, is you can organise the operator product expansion in a very clean way, which means you don't have to remember anything. Seems that I can't remember anything, but this is easy enough to remember. So you can just expand out what that is. So V of A Z, you write as sigma AN Z to the minus N minus 1. But that's in the range Z is greater than Z minus W, or W is greater than. That's it. That is your vertex operator algebra. And that's enough to get it. So, in fact, there's the sum, the tricky step, which requires, it's purely algebraic, is just checking that if, in this sense, we have this kind of locality of commuting in the sense of analytic continuation, that if these commute, or greater commute, in the sense of analytic continuation, then so does this. So just, and that's, it's not hard to prove, you just got to keep, it's half a page, and it's more or less, it's not hard, you just have to be convinced. It's called Dongslam, but it's much easier to prove the Dongslam because you can do it. Dongslam is kind of done in a strange way, whereas if you just think of these as formal tower series, it's very easy. Okay, so that's it. So now, then, for example, so the primary field for the state E minus 1, oh, sorry, so the vector here, the vacuum vector, will correspond to the identity operator, unsurprisingly. The vector E0, wedge E111, will correspond to psi Z. C just wedges by E0. When you can just see that it creates that thing. And then E minus 2 wedge E minus 3 will correspond to psi star. Well, now I can tell you what primary fields are in this picture, and it's in general true if you work with intertwiner things and modules. It's just with the same thing with bells on. So primary field you left because you didn't like my definition. No, I don't. I just arranged to tell a lie. You ruined it. So a primary field, in this case, is something which is a bit like the vacuum. So the vacuum, well, so, and if I take a vector A, such that L n of A is equal to 0 if n greater than 0. Well, I've written down 3 vectors which satisfy this, and then V of A Z is the primary field. In fact, in this Fox space model, so there is a little paper on that, all the primary fields can be described explicitly by the formula of Jeffrey Goldstein. But the ones we need, therefore, the only interesting identities not interesting are psi Z and psi star Z.
I think as you told us to have the definition. You said
That is the definition of primary field. Yes. So, I mean, in general, that would be the correct definition. And there is this definition can be taken, I would say this is an operator value distribution. You can think of this as being tensoring projective representation by an action of the diffeomorphism group on densities into another projective representation. That can be interpreted as that. And then because of this condition, that means it's equivariant for the action of the diffeomorphism. So that's another, this has an immediate link to an analytic definition, which is sort of the one used in the fusion paper. Right. Okay. Now, so in the last quarter of an hour, I've said what confusion is. It involves primary fields and sorting things out. Segal fusion, I'm just going to say that it corresponds to the operator given. I gave an operator. I said that this operator here, this if I take the Hardy space, then this defines an operator from F tensor F to F, just by the processes I mentioned yesterday. And now I want to say why this thing here is just a primary field. It is just why it contains all the, it is essentially the same as this. Okay. So what does that mean? Well, if I plug in an A here, so I have an operator T, and then I can take T of psi tensor A, then I claim that this is the same with Q to the L0, and this is going to be slightly wrong, but only slightly. So I'll do it like this. So I'll move the circles so that Z is here, and there'll be another Q to the L0 in there, which I've omitted. So that says, so this operator, which was just defined using analysis, if I write it down this way, is just essentially this vertex operator. But that's somehow what's supposed to go on in conformal field theory, that you chop a Riemann surface up into little pairs of pants. I'm not doing this very well. So this is chopped up into pairs of pants annually and little caps, a little cap at the end. I did actually need the cap. And you can actually have more points on here. If I wanted to mark a point with a projection, then taking a disk, I'd mark the point. And the projection is going to either be labeled by a plus or a minus one, depending on whether it's the two primary fields. Psi will be a plus, and psi star will be a minus. And then what I can do is I can ask, instead of taking the Hardy space for this disk, I can take the Hardy space for the disk where I take boundary values of functions which vanish at that point, or which have a pole at that point. Of order 1. And that will also kind of give me essentially asserting a field, one of these two, in this sense. So that's all part of this picture. So you ask for a pole, or a zero, simple pole, or zero at this time. That's a straight translation of this picture. If you think about the Hardy space decomposition, here we've allowed in the complement. If you think about how we define the Hardy spaces for the complement, one introduces we allow 1 over Z in the complement for one of these here, perhaps 1 over Z for this, and then everything vanishes here. We take the complementary thing from Hardy space, which these two move. See what I mean? Here, the Hardy space will be E minus 1, E0, E1, so we've allowed a pole, Z to the minus 1 is E minus 1. And here, we just allow all the things have to vanish, that we're going to get Z, Z squared, Z cubed, etc. And That's exactly the translation fits. Okay, so how do you prove, the question is, how do you prove this? Well, I've kind of set up everything so that it kind of works. Here, with the vectors that correspond to this, because of the way I defined the complex structure on the Grassmannian, they were given by these Cauchy kernels, and the kernel operators as Z moves around will vary holomorphically with Z. So that's a holomorphic family. Also, the way I set it up, rotations, it'll be compatible with rotation. So rotation will act on here and here, not on here. So that will be, so in some sense that's, so now I insert a vector in here, and then, so the two ingredients. So first of all, the vacuum vector for a projection P or E, non-self-adjoint, is specified. Let me just say the P, but you can do the same. Is specified by A of F omega P equals 0 for F perpendicular to pH. And A of F star omega P equals 0 for F in pH. That specifies the vacuum up to a scale. And well, then that implies that when I put the A's in, I get a commutation relation for this operator. So that gives, this implies a T, some commutation relations with AFs and AF stars. So I'm not going to specify, but you can see that because these, this was as that was as a vector. This is now as an operator, and so it will just translate it the way you identify Hilbert-Schmidt operators with vectors, then the action is going to become something on one side and something on the other side. So it becomes a commutation. So then, punchline is that the vertex operators, VAZ, are also specified by, well, L0 VAZ equals Z d by dz plus alpha prime VAZ. And then a formula used in Richard Borchers. Borchers commutator formula. But what you do is you take VAZ, VBW, just that thing, you take a matrix coefficient, you multiply it by Z minus W to the K. And you treat W as fixed. And then call this FZW. And then this is and then you so this is the circle Z minus W equals delta. This is the circle Z equals R less than W. I'm not going to say these. And then this is the circle Z is R greater than W. Obviously, Dutch and R are related. Well, the point is, if you integrate this function, which is rational with no singularities, round here, you get 0 by Cauchy's formula. But, I mean, it's a rational function, so you don't really need Cauchy's formula. If you write that out, so if you write out that contour integral, then that implies that you get an bw minus bw minus plus or minus bw an is equal to the sum of k greater or equal to naught, and choose k, a, k, b, so that's a product w to the n minus k. That's only a finite sum. So what this says is, in order to generate the vertex algebra, you just first of all have to check for fermions, that you create fermions the right way. And then the other action of fermions, by this commutation relations, will then, as the states grow bigger, because of Borchert's commutator formula, will create all the other states. So that's kind of the way it's done. So the operator algebra formula for the vacuum, combined with Borchert's commutation formula, which tells you how you create more and more complicated vertex operators corresponding to higher energy states, are compatible. That's it.
So you're trying to show that, lost this bit, but you're trying to show that this operator.
You're trying to show these are equal.
Right.
So you check it for a lowest energy state. Just, I mean, I think that if you put the vacuum in here, that just essentially removes this circle. So it's obvious. And then you just, then in creating the states, these commutation relations plus the Borchert's formula together will allow you to check that as you do that, you get the higher and higher states. I don't know if there was an easy way of doing it than that, but that, you have to do some way. And then you can play all sorts of games. After that, then this game of whether confusion and Segal fusion. I mean, so the idea then. So let me just say what I think is true. So switch off the computer. So in fact, what you want to do is get curves, foliate the inside of the disk with things which grow out towards the boundary. But that is not very hard to do, so this is undergraduate mathematics, depending on which university you're in. D is equal to 0. So that's just, there's a conformal transformation which takes D to 0, which is because D is equal to, this is equal to L, and that's equal to minus, and that's equal to that. Right, so this is, this semicircle is the same as the quarter plane, and then by Z goes to Z squared, this is the same as the half plane. And then by the Cayley transform, this is the same as this. Right. Well, here, it's pretty clear what you do. You could just take concentric circles going out. And that will therefore define a very nice family here, which is actually amenable to analysis. That you can actually do a theorem of Kerber, which is quite hard to prove, depending on who you are, but is that this, each picture like this, will look like this. I mean, that's just, it's the Kerber uniformization thing for triply connected regions.
Well, these are circles.
These are circles, so everything can be mapped onto a circular region. But here, what sort of happens is if I want to just put fermions on here, I mean, I can actually, because of the way the conformal field theory goes in the gluing, we can actually write down this function as just a function of work. If I put a fermion here, upside here, and upside star here, then I can work out what a smeared fermion on the boundary looks like, and a smeared fermion on the boundary there looks like dual fermion. Then, so if I take them concentrated in this interval and that interval, then it's essentially a double integral of, call this f and g, f say GW z minus w dz dw over these two contours. But you see, as the contours go out, so I'm prepared, this is a dense set of vectors, by the way. Fermion, I can produce a product of fermions if I like. What will happen is that then I'll have something on the outside here, a fermion psi of f, and a fermion psi star of g, and that's almost what we have in confusions. So in this simple case, of course, I have to take more complicated things. I have to take more points inside here. So perhaps a product of fermions, in little intervals broken up on the circle and be pretty well here. The same game will work because these product, in a physics book, you open a physics book, that formula for a product for an endpoint or two endpoint function of fermions, and then size here and size stars there will equally well mix is completely known. That's, I think if you don't know that, you can't be a physicist, so I can't be a physicist. So that I think, so that's my idea, is it's very simple and stupid in this case. That is probably the key to doing this in the case to show that you can kind of, in the limit, Segal, with these special prepared states, the Segal fusion, or the operators, intertwining operators of Segal fusion, tend towards something which can be easily recognized within Hom fusion. And I think that clearly what I've said here, it uses language of primary fields, endpoint functions, ... So that language is common to conformal field theory at all possible levels. By the way, to construct the vertex algebra for SU2 at level K, just take the tensor product of this fermion algebra, and then you can see the SU2 fields inside it, take the subalgebra generated by SU2. So you don't do, once you've done the work for that, you've done everything. So I think, at least that's my feeling at the moment, that's more or less how that should